Hello everyone. In this video, I am going to talk about section 4.9, reduction of a simple distributed loading. In the real world, many times, quite often, we see distributed loads. So a surface area of a body is subject to a distributed load. So the load is being applied, not just a point, but being applied to the whole surface. So such forces can be caused by wind, fluid, or the weight of an item on a body surface. Well, we will analyze the most common cases of a most common case of a distributed pressure loading. This is a uniform load along one axis of a flat rectangular body. In such case, W is a function of x. So, in other words, it also has a unit of a force per length. So remember, the unit of force is Newton or pound, right? So unit of force per length, that says it's going to be Newton per meter or pound per inch, something like that. Consider an element of the length dx. The force magnitude dF acting on it is given as dF equals Wx dx. The net force on a beam is given by Fr integral over the entire length dF, and also it can be also written as integral over the entire length Wx dx, which equals A, where A here is the area under the loading curve. This goes together with your calculus. Integral will be the area under the curve. The force dF will produce a moment x dF about 0.0, and the total moment about 0.0 is given as MRO equals over the integral over the entire length d x dF. And then also over here, because from the previous slide, we learned that dF will be W dx dx, assuming that this resultant force Fr acts at x bar. This x bar right here represents the center of gravity of this area. Okay, so it will produce the moment about O as x bar Fr, resultant force. So overall, x bar, we can take it out of the integral, and the inside the integral will be W dx, Wx dx. Consider comparing the last two equations that we talk about, put them on the numerator and denominator. We can get this equation right here, x bar equals integral over the area dx dA over on the denominator, integral over the area dA. So later in the chapter, the next chapter, there will be one chapter we're going to talk about the center of gravity. You will learn more detail in that chapter. But right now, Fr, which is the resultant force, acts through a point C, which we call this point C the geometric center, or the centroid of the area under the load curve, Wx. Let's take a look at some examples more specifically. And for this, for now, we're gonna only looking at the rectangular and triangular loads because they are simple geometric shapes. First one over here, for example, it's a rectangular load. We know that for rectangles, the center of gravity is right there in the middle. So to replace this distributed load, if I want to use one single load as the equivalent force to replace that distributed load, rectangular one, the one on the top, that will be the location will be right there in the middle of the rectangle. So over here, overall, I have 10 feet. So meaning the equivalent force will be right in the middle where 5 feet. Okay, and the magnitude will be the area of this distributed load, the area with a quote, right? So 400, I got 400 pound per foot. Total, I have 10 feet. Multiply that together, okay? That feet cancels out. Your unit end up with 4,000 pound. The unit will be pound. Multiply that together. So, excuse me, for this rectangular shape of distributed load, the length is 10 feet and then the width is 400. Okay, length multiplied by the width gives me the area, and that area is the magnitude of the load. Looking at the triangular one, if I'm looking at a triangle, we know that the area of a triangle, it is not just simply the width times length, right? It's 1/2 base times height for the area of the triangle. So over here, your base is going to be 6 meters. The height is going to be 600 Newton per meter. So in order to find the area, that's going to be 1/2 times 6 meter times over here is 600 Newton per meter. So these together, that will be 1800 Newton, meter in per meter. Meter in per meter cancels out. That's where that 1800 Newton comes from. Now, that's the magnitude. Locations of it, we talk about we talk about if this thing is a rectangle, it will be right there in the middle. Under the condition is a triangle, it will be 2/3 from the top and 1/3 from the base. Overall, this thing's got 6 meters. That means 2/3 of that 6 meter gives me 4 meters. That's where that 4 meters comes from. The center of gravity, centroid uh, of this triangle will be 2/3 from the top of the triangle and 1/3 from the base of triangle. So 1/3 of that 6 is 2 meters. So down here is going to be 2 meter. Overall, we have 6 meters together. Okay. And then so there's a bunch of calculation that I just went over. And please note that centroid of the right triangle is at the distance 1/3 of the width of the triangle as measured from its base. Example number 2, I have a combination of triangle and rectangle. So what we're doing here is that I am going to do the equivalent. I'm going to break it here. I'm going to break the triangle on the left plus a rectangle on the right. Rectangle, I have an overall force. Magnitude is going to be the area. Location will be right in the middle of that 8 feet. And then the triangle one, I'm going to do the overall. Again, magnitude is going to be the area of that triangle, 1/2 base times height. And the location will be that 4 feet, where 4 feet is 2/3 of that 6 feet. So it will be 2/3 from the top, or 1/3 from the base of the triangle. So that's where that 4 feet comes from. Now be careful. This in the middle, this FR2 resultant force, FR2, it's in the middle of that 8 feet, meaning it's 4 feet from point B and it's 4 feet from here. So if you want to know how far that FR2 is it away from point A, don't forget to add that 4 feet to that 6 feet of where that triangle is. So that 10 feet needs to be, yes, it's 4 feet. Yes, it's a minimum in the middle, but it's the middle of the rectangle. From that point A, you have that 6 feet plus the 4 feet, which is 10 feet total. Knowing the location and the magnitude of the equivalent point load to replace with that distributed load, we also can calculate how much moment is generated about point A. Okay, about point A, I know my resultant force 450. Resultant force is 450 for FR1, 1200 Newton for FR2. So 450 is generating a moment about point A. magnitude of the force times the distance. Distance is going to be 4 feet. And the other would be FR2, magnitude is 1200 times the distance, which will be 10 feet. Both of them are generating the moment. This is the moment overall generated by FR1 and FR2, or you can say by the distributed load as well. So this is the equivalent so the moment about point A. And then since the moment about point A equal to the magnitude of the force, magnitude comes out from adding the FR1 plus FR2, magnitude times the distance. We know the magnitude overall. We know the force overall. We can calculate the location. And this location will be X bar will be the equivalent force location. So in other words, I have F what I have FR1 and FR2. If I'm going to use one single FR to replace FR1 and FR2, the magnitude will be 1650 pounds and the location will be 8.36 feet away from point A. Where does the 8.36 come from? You're solving this equation right here. We know the magnitude total 1650. We know the moment total is 13,800. Okay, and we can calculate the X bar, and that X bar will be the overall location. So this diagram, first diagram says I got two. One represents the triangle portion, one represents the rectangular portion. And over here, I have FR being I can find one force. I can find one force to replace FR1 and FR2 together, one single force. Magnitude is 1650. Location would be 8.36 feet away from point A. Group problem. So I have this one right here. I got two triangles, right? We're going to look for we're going to have two equivalent forces to replace that triangle. Magnitude will be the area of the triangle, 1/2 base times height. And then the location, again, it will be 2/3 from the base. Sorry, 2/3 from the top or 1/3 from the base. Now be careful where your reference point is. For each of the triangle, this is 1/3 of 7.5. And this part here is going to be 2/3 of 7.5. Okay, same thing similarly. This portion is going to be 1/3 of 5.4, and this portion here is going to be 2/3 of 5.4. Okay, that's that where that comes from. And then if you're using that point O as our reference point, be careful, especially the second triangle, right? It will be 1/3 of 4.5 plus the length of the first triangle plus that 7.5. That's what's going on over here to find the actual location of x2 bar. X2 bar. Okay. Now adding all of the forces together, we got FR1, FR2, and don't forget that 15 kilonewton that is being applied. That's a point load being applied to the other side of the beam. Overall, I have that force, and every single one of them, all three of them, is generating moment. So that 500 moment is at point O, and we have moment 1, moment 2, and then that moment is generating by that 15 kilonewton. Together, I got this much moment. Together, I got this much force. If I know the overall force, if I know the overall moment, we can find the location. We can find the location. Okay, so that location, well, it's not written. I wish they keep writing. So if they need it, well, equivalent force, couple moment. Oh, sorry. This problem, we're not looking for the actual location. We just need the equivalent force and a couple moment. Okay, that's all I want to share with you today. Hope that helps you. Any questions, please let me know. And thank you for watching.